Good afternoon, folks. Welcome back to another CS128-Honors lesson. Today we'll be finishing our discussion on parallelism and concurrency, and without further ado, we'll go ahead and get started. So, the topics for today are first to review, and then we'll discuss this shared state concurrency, which will contrast a lot with message passing concurrency, we'll call it, or concurrency by passing messages through these channels that we just learned about. This is actually going to be our last lecture on parallelism and concurrency. So after this, we'll have one lecture this Wednesday by Matt on sort of templating, which might be very helpful for certain projects. And then we'll move into the final project territory. Some quick reminders: MP2 is due not this Friday, but next. We're going to be releasing more information regarding the final project tomorrow, so keep an eye out for that. Basically, a short summary is that we're looking for groups of 2 to 3 people. You'll be able to work on whatever project you'd like. We're here to help guide you. We encourage you to, do this locally. I mean, it's not like we're going to have a Prairie Learn for this. Be developing locally. Use GitHub if you're familiar. I believe that in your main 128 course, we did actually share some Git lectures way back when. Collaborate with your team, use packages, or rather, I should say, use crates. Utilize, we saw yesterday, or not yesterday, last Wednesday, we saw this example of sort of a, the Julia set printing thing. That would be, maybe a sufficient final project. I mean, you use a wide variety of different packages in that project, and you do something super, super cool and super applicable. I think that would be great. So yeah, just maybe an easy example there. Of course, maybe you'd want to extend it more, maybe you'd want to extend it in a different direction. That would be kind of up to you. But yeah, I think that one would probably be sufficient just because it is sort of extremely math heavy. Additionally, we'll be sending out a feedback form in the coming days. I highly encourage all of you to fill this form out. We will be making it anonymous, but we'll also be granting extra credit for it. And the way we'll do this is if some percent of the course fills this out, then everyone will get probably like 1 to 2% extra credit on their final grade. So please fill this feedback form out. This kind of midpoint feedback form will focus more on, what you thought about the homeworks, the MPs, and the lectures. Any feedback that you might have is, of course, incredibly helpful. This course is brand new. All of this was developed sort of this semester for y'all, so we'd love to hear your feedback, what you like, what you didn't like, favorite lecture, least favorite lecture, stuff like that. So please fill this form out. If not for the extra credit, then for building this class to be better and making it better for future students. Of course, it's all student run, so yeah. At the end of the semester, we'll have a second feedback form. This one will probably be worth like 2 to 3%. This one will be a little bit longer than this halfway one, and we'll encourage you to fill that one out as well. But we like to have a feedback form kind of halfway through the semester while this is all fresh in your minds. Okay, so let's begin our review today. We learned probably 2 weeks ago about why we actually care about this sort of thread-based processing and parallel performance or concurrent performance. And one of the major reasons is we've seen, I'm an ECE major actually, not even CS, and so I always, this is kind of my fun example I like to say is, we're doing our best over here, designing CPUs to run faster, to run your programs faster. However, there's a limit, right? I mean, we can't really beat physics. It's very, very hard to increase the frequency any further than we've gone, with the exception of like liquid nitrogen cooling, in which case we can go from like here to like here. But still, this is not sort of the linear pattern that we saw many, many years ago. Or sorry, I guess this would actually be exponential because this is a log base. In either case, what we've seen is sort of the single thread performance of programs is slowly starting to dwindle, right? I mean, it's slowly increasing still. However, it is increasing much more slowly than in the past. And so one of the major ways to make your programs efficient for the future, to make it run 10 times faster on hardware that should be 10 times faster, is to make sure that you're utilizing your available cores, which are still increasing. Now, I could go into a longer discussion, like logical cores are eventually going to go something like this, but that's for another day. And maybe if y'all choose to take computer architecture courses, it's for that day. In either case, making sure your programs run efficiently, making sure your programs are effective for the future, that they're going to be used in 5 years, 10 years, 20 years, is largely a question of, are you using all of your available cores? And if you are not, then why? Why not, huh? And so to begin our discussion, we learned about how to create threads in Rust. And of course, just with the standard library thread create, we can call thread.spawn. This thread will execute the closure within here, passing any variables we might like through this, or using the move keyword that you learned about with math. If we remember from this specific example, we don't call this handle.unwrap, and so this thread might, not finish its execution before the thread is, or before the main thread kills it. So this might get to, 4, 5, that was a 6, 4, 5, 6, something like that, before it runs out. But of course, we don't quite know, right? For some reason, if this main thread doesn't get scheduled for a while by the operating system, and this spawn thread gets scheduled a lot by the operating system, it could get to 7, 8, or even 9. But yeah, it's just a matter of sort of how the operating system is feeling that way. And that also maybe mentions why sort of using this unwrap might be very valuable. We learned the difference between concurrency and parallelism. Parallelism being often you're accomplishing several tasks at the same time. Concurrency being, while you might be stalled on one task, maybe right here you're waiting on some data from memory that's taking a while to get there, you can swap and go work on a different task. Of course, this swap is not free. There are things that come with it, but or some expenses that come with it. But I won't get into that. That's not really the topics for today. If any of you are interested in all of sort of this stuff, like this has to do with like caching and more hardware level stuff, some operating system level stuff, I don't know, just shoot me a message. Always happy to talk about it. We learned about what it means to pass messages in Rust between threads, essentially using messaging as a opportunity to have threads coordinate more effectively. And so rather than sharing memory, what we do is we communicate across this thing that we call a channel. Channels have transmitters and receivers, like the MPSC channel, multiple producer, multiple transmitter, single receiver, single consumer. And of course, that single consumer very often is going to be our main thread. These producers are going to be the threads we spawn. And basically, the main thread sort of works as this coordinator between the other threads. And a quick reminder, channels close if either of these are dropped. And we looked at a very basic example of this, spawning some channel, or rather creating some channel, spawning some thread, sending some value over the thread channel, over the channel. The main thread gets here. This is, of course, blocking, right? If we remember the non-blocking one, it was receive try. It'll wait for this value to come in, and then it'll say, hey, I got it, we can move on. Additionally, we looked at, some examples cloning these transmitters, right? The whole multiple producer idea. Creating multiple threads. One thread here saying hi from the thread. Another thread saying more messages for you. And then in our main thread, waiting to receive all of these. And printing them out as we receive them. Eventually, of course, these will get dropped because they'll go out of scope. And we learned also, maybe this important quote that I'd like to reiterate of do not communicate by sharing memory. Instead, share memory by communicating. Basically saying, hey, we looked at all these issues with having some piece of data and having maybe multiple threads attempt to read and write that data at the same time. Live lock, deadlock, starvation, all these other ones that we looked at a couple lessons ago now. And those exist, but those don't exist when you use messaging. Of course, messaging has its own cost. It's a little bit slower, and sometimes it can be a little bit, I'll say, stranger to implement. right? You have to, sort of think a little bit harder about how you're using this messaging that's going back and forth. But, it is still valuable to know what is sharing memory. What does sharing memory look like? And you looked at this a little bit with Matt, with mutexes, and we're going to look at this more today. And actually, this will be the finality of this lecture. We'll just be looking at this sort of shared state concurrency. We'll look at some brief examples, some that work, some that don't work, and why. And that'll be it for parallelism and concurrency. So what does it mean to share state? The idea behind sharing state is that multiple threads, of course, can access the same data at the same time. Or at least that's the idea, right? Maybe I shouldn't say same time. Maybe we should say very similar times, because one of the problems that we'll quickly run into is that when multiple threads access the same data at the same time, awful things can occur where we sort of get these race conditions, is what we call them. We're not sure these two threads are trying to do something at the same time. Whichever one gets there first is going to change the outcome of what occurs, which of course is not something we want in a computer. It's not deterministic. We can contrast this behavior to messaging, where we're using these channels and we're transferring ownership of the data back and forth. And you briefly discussed this idea of mutexes. Mutexes standing for mutual exclusion. Of course, sometimes with these, I'm not quite sure what to call it when you cut words in half in portmanteaus, I believe. Anyway, with some portmanteaus make sense. This one to me never made sense. Mutex, mutual exclusion, that doesn't fit together as well as I feel like it should. In any case, it's a method of controlling access to data. When a thread wants to access some data, so let's say we have thread A and thread B, and we have some data. I'll just call this data. When thread A wants to access data, it must first lock data. And then once data is locked, it can go and interact with data. It has access to sort of the value here. Maybe it's not a great thing to draw these as two separate things, but in a way they sort of are, the mutex and the data. And maybe, it wants to rewrite this value. It wants to change it to a 6. Maybe it wants to change it to a 7. Who knows? And then eventually when thread A is finished with this data, what it needs to do is it needs to unlock this data. And so now thread B, and then it says, okay, I no longer need this. Thread B will go and request access to this mutex. It will lock data. It will go change this to, I don't know, let's just change to 15 so I don't have to erase things. And then it will be done. It will unlock the mutex and it will move on. Of course, an important property is if something is accessing this mutex, is interacting with the data, and thread A attempts to, it's going to be blocked. Right? You can't work with data that's behind a locked mutex. That's the whole idea of the mutual exclusion. In modern programming, especially in languages like C, managing mutexes is actually a little bit of a pain, I'll say. It can be a little bit annoying because you have to sort of keep track of all of these different edge cases. And one of the key ideas being you don't actually know when certain things are going to occur. And so, you might be, if this is your code block in thread A, you don't know which of these lines you're going to sort of be requested for that data for, right? And you could be in the middle of some operations that's sort of very important. And then, bad things can happen. We looked at this one example a couple lectures ago where you'll get some value. We'll just say x equals get data. Well, okay. Anyway, you get the data, you get the value of some data, which might be 5, and then some other thread goes and changes it to 6, but then you wanted to increment it by, or decrement it by 1, and so you want it to be 4. Well, the question is, should this be 4 or should it be 5? Because 6 minus 1 is 5. Who knows? No right answer. But we can look at some brief examples of using mutexes in Rust nonetheless. This is, of course, the most basic example. We have a single thread using a mutex. We'll import our mutex. We create a mutex with some data inside it that we'll call, I don't know, this is just the data inside the mutex. And then we'll open up a level of scope here. And the reason we'll do this will be discussed in just one moment. And what we'll do is we'll reference this mutex. We will lock the mutex, and we'll unwrap. Why do we unwrap? To catch any errors, of course. And then once we have this data, we have it in num, we can dereference num, change the value to 6, and move on with our lives. You might say, Eustis, you just had this whole discussion on you need to unlock the data, but we're clearly not unlocking the data. You'd be correct. However, sort of this num that we're returned with is what we call this sort of like mutex reference. And when this goes out of scope, of course here, when this value is dropped, remember we discussed from, maybe ownership, many lectures ago, when variables go out of scope, their value is dropped. Literally, the drop function is called on them. That automatically is going to unlock this mutex. So we don't really have to worry too much about this. Of course, this code works exactly how we'd expect it. This is only read one thread, so we don't have to worry about much. But of course, we can do it with multiple threads. We'll import mutex in thread. We'll create a mutex with some value 0. We'll do a counter, just counting up between threads. Maybe some event is occurring and we'd like to know how many times or go until a certain time. And so we'll build a short for loop. In this for loop, we'll spawn some thread, moving any data necessary into the thread. We'll unlock the mutex, the counter mutex, unwrap it, increment the number, and just keep track of the handles. That's all this is doing. And then eventually in the main thread, we want to wait for all the handles to finish and print the resulting value. So my question to you is does this code work? Are there any issues that you might see? And of course, this code wouldn't work. We're using this move keyword, and this is a little bit sneaky. We're using this move keyword, and so we're moving this counter variable into the thread. But of course, we're spawning 10 threads, and so it might be actually sort of quite difficult to transfer ownership of the counter to the second thread if we've already given it to the 0th thread, or the first thread, I should say, maybe. And so, obviously that this example would not work because of that sort of ownership idea. So instead, what we can do is we can have this thing called a reference counter. And basically, this allows multiple ownership. It's just another way of doing it. We have sort of one piece of data here. And so now what we're doing is just kind of creating references to this data and transferring those references to things. This is totally allowed. And so in this example, we wrap our mutex on a reference counter. Same thing, for loop. Before we transfer ownership, we're going to clone the counter. So create a new reference for this thread, transferring ownership of only that reference into the thread, and doing the same behavior. So my question to you is, does this one work? And this one's a little bit sneakier. I wouldn't expect all of you to get it, but it actually does not work. And the reason for this is sort of in the behavior of reference counter. And once again, I wouldn't expect you to know this off the top of your head, but basically when we're performing this reference counter, this still runs into the issue of race conditions. We don't know when one thread, if we take this dereference num plus equals 1, this is really when it comes down to, CPU instructions, something along the lines of get the value of num, increment the value of num, and load the value of, or store the value of num back in to some memory address. And of course, my question to you is, we execute this get value of num, and maybe we even execute this increment value of num, and then the CPU goes and works on a different instruction. And on that different instruction, it gets the value of num, increments the value of num, and stores the value of num. Well, clearly what has happened here is we've stored, maybe previously num was like 3, and now it would be 4. This other thread, also loads in a 3, also increments to 4, and stores 4 back in. And then when we go to store num, we're also storing 4. So we've lost an increment. And what we call this is this operation here needs to be what we call atomic. It either needs to happen completely or not at all. And this is, this gets into a much larger discussion of sort of atomicity and concurrency, and I can't remember there's a keyword or an acronym. Atomicity. I can't remember it. Google this if you all are interested. This has to do a lot with like databases and honestly computers as well. Atomicity, like the ability to be atomic. This one is consistency. I can't remember the other two. Shame on me. In any case, we know that this one doesn't work. And so what we'll do is we'll turn this reference counter into an atomic reference counter. The only difference being when we're doing these operations, sort of they're safe. They're what we call thread safe. And so we can remember, reference counters are good for multiple ownership, and atomic reference counters are good for multiple ownership on multiple threads. And this is really what sharing memory is going to look like, using something along the lines of an atomic reference counter, using your mutex, in order to just make sure that they're behaving nicely. And you can see, this is a little bit sneaky. I mean, I wouldn't really expect many of you to be able to predict that like this reference counter does not behave atomically unless you sort of already knew what atomically meant and you looked up the documentation and you explored it, which is a difficult thing that you can easily miss, right? And so this is why we maybe prefer messaging a little bit better. That being said, shared memory has its benefits. It's pretty fast. Actually, it's extremely fast. Both of these things are relatively fast on the grand scheme of programs, but when you're doing these operations a lot, it can really add up in terms of messaging rather than shared memory. But of course, shared memory, this does not solve our issues of deadlock, for example. If, for example, rather than incrementing the number by 1, we had some big for loop or while loop, and just by chance, like this while loop never completed, none of the other threads are going to be able to do anything. They're all going to be sitting right here. And so, there's definitely downfalls in this too. Nothing is perfect. But that's all for today. Less content today, more discussion on sort of recap and other stuff. But I really hoped y'all enjoyed sort of this discussion on parallelism and concurrency. I highly encourage you to use it in some of your final projects. I'm a huge fan, so if I see some parallelism and concurrency, I'll probably be biased and lean towards giving you some extra points. But that's not to say that if you choose to go a different route that we're going to grade you any more strictly. Of course, it just depends what you want to do. And so I'm super excited to see all the projects that y'all come up with. I can't wait. Anywho, I'll see y'all later. Have a wonderful rest of your week, and bye-bye.